Hello everyone, this is the seventh and the last video for the series of videos on the chapter Light, Reflection and Refraction. In this video, we are going to talk about the lens formula, magnification, then power of a lens, and we will also solve some numerical problems on the lens formula, magnification and power of a lens. So let us first start with the lens formula. You people are already aware of the mirror formula. We discussed that when we were talking about the mirrors. So here we are going to discuss the lens formula. The lens formula is 1 upon V minus 1 upon U is equal to 1 upon F. Here V is the image distance, that means the distance of the image from the lens. U is the object distance, that is the distance of the object from the lens, and F is the focal length of the lens. So please remember that this is the lens formula. There's only a difference of one sign between the mirror formula and the lens formula. In case of mirror formula, it was 1 upon V plus 1 upon U, but in case of a lens formula, it is 1 upon V minus 1 upon U. So please keep that in mind. Then as far as magnification is concerned, there are two formulae for magnification. The first one is the height of image upon height of object. In certain books, you will find it written as h dash upon h. And the second one is V upon U. Now, if you remember, in case of mirrors, it was minus V upon U, but in case of lenses, it is V upon U. As always, V is the distance of the image from the lens and U is the distance of the object from the lens. HI or H dash represent the height of the image and HO or H represent the height of the object. But it's not all like about the distances. We also have to use the conventions about which we'll be talking in just a moment. But before that, let us know what is the power of a lens. So many of you must be using spectacles, and whenever we wear spectacles, we use a lens of a particular power in that. So what is actually the meaning of power? It is the ability to converge or diverge the ray of light that falls on a lens. So how much light does a convex lens converge, or how much light does a concave lens diverge? That is the power of that particular lens. So if you have to calculate it mathematically, the formula for power is 1 upon focal length, but care has to be taken that in this case the focal length always has to be in meters. So it's 1 upon focal length in meters, and the unit for power is diopter. So the power is always measured in a unit known as diopter, which is represented by the letter capital D. Conventions stand as always. Since a convex lens has a positive focal length, because the conventions are the same way as was in case of mirrors. Since the focal length of a convex lens is on the right hand side, so it has a positive focal length, so the power will also be positive. Whereas in case of a concave lens, the focus is on the left hand side, so the power will also be negative. Now a brief look at the sign conventions. They are almost similar to those of mirrors. All the distances are measured from the optical center in case of lenses. Distances measured in the direction in which the light travels are positive. Distances measured in the direction opposite to the direction of light are taken as negative. Above the principal axis, positive. Down the principal axis, negative. So these are the sign conventions. So we can understand this with the help of these two figures. The first figure that you see, this is a convex lens. So for a convex lens or for a concave lens, that is the second one here, this is a concave lens, U is simply negative because we always place the object to the left hand side. So U always is negative. You don't have to give a second thought to it. Then what about F? For a convex mirror, focus lies on the right hand side, so F will be positive. But for a concave lens, focus lies on the left hand side, so F would be negative. Also for V, in case of a convex lens, we know that images of both kinds are formed. So if the image is positive, what does it mean? And if the image is negative, what does it mean? Positive image means the image is formed here. It's going to be real and inverted. And negative means the image is going to be virtual and erect, because the image, if it's a negative, is formed on the left hand side. Also for a concave lens, the image is always negative, because for a concave lens, we know that the image is always formed on the left hand side. So these are some conventions that we use for lenses. Let us now solve a few numericals. Let us now solve the first numerical problem. A 6 centimeters tall object is placed perpendicular to the principal axis of a convex lens. So the height of the object here is given as 6 centimeters. The convex lens has a focal length of 15 centimeters, and we know that since it is a convex lens, the focus lies to the right hand side and it's going to be positive. The distance of the object from the lens, that is u, is going to be 10 centimeters. So according to the convention, u is always negative, so I put a minus sign here. You have to find the position, size and nature of the image. So the formula that we are going to use is obviously the lens formula, which is 1 upon v minus 1 upon u is equal to 1 upon f. So if we modify it according to the question, we have to find out v over here. So it becomes 1 upon v is equal to 1 upon f plus 1 upon u. Substitute the values in this. So we get 1 upon v is equal to 1 upon 15 plus 1 upon minus 10. So when we simplify this by taking the LCM, we get this equal to minus 1 upon 30. So that means v is going to be minus 30 centimeters. So what does this tell you about the nature of the image? A negative v tells you that the image is formed on the left hand side. And if the image is on the left hand side in case of a lens, it is always a virtual and erect image. So that is the nature of the image in this case. It is going to be a virtual and erect image. So the first part is answered, position. The third part is answered, the nature. And now we have to find out the size. So for finding the size, we will use the formula from magnification, that is height of image upon height of object is equal to v upon u. Again, we modify this formula according to our requirement. We have to find out hi, so it becomes v upon u multiplied with the height of the object. Substitute the values here. V is minus 30 that we just calculated. U is minus 10 and the height of the object here is 6. So this minus cancels with this. This cancels with this and we are left with the 3 here. So 3 times 6 gives you 18 centimeters as the height of the image, size of the image. So again you are getting a positive height of the image. This again confirms your nature of the image. It's positive, so it has to be erect, and virtual is always erect. That means the nature is virtual and erect. So this is how we solve such questions. Let us now have a look at the second one. Now in the second question, an object of height 5 centimeters. So the height of the object here is 5 centimeters. Is placed perpendicular to the principal axis of a concave lens. So this time the nature of the lens is concave. So the focal length is going to be negative 10 centimeters. Remember, for a concave lens, we take focal length as negative because it's on the left hand side. If the distance of the object from the optical center of the lens is 20 centimeters. So the distance of the object is 20 centimeters and we know that u is negative. So I have already placed the minus sign before it. Again, we use the lens formula, that is 1 upon v minus 1 upon u is equal to 1 upon f. We modify this formula according to our requirement. It becomes 1 upon v is equal to 1 upon f plus 1 upon u. We substitute the values in this. It becomes 1 upon v is equal to 1 upon minus 10 plus 1 upon minus 20. And when we simplify this, we get this equal to minus 3 upon 20. That means our v is what? V is 20 upon 3 negative. That makes it minus 6.66 centimeters. Now what does this tell you about the nature of the image? It's a negative sign with v, which shows that the image is formed on the left hand side. So it's going to be a virtual and erect image. That is going to be the nature of the image here. It's a virtual and erect image. Now we also have to find the size of the object. So as earlier, hi upon ho is equal to v upon u. We are equating the two formulae for magnification. So hi becomes v is minus 20 by 3, because whenever we need to simplify it further, I always prefer to take it in a fraction and then solve it. And u is minus 20. So when we simplify this, 20 cancels out with 20 and we are left with hi equal to 1 upon 3. That is a positive 0.33 centimeters. So it's a diminished image. Since it's a concave lens, we all know that the image formed is virtual and erect and diminished. So this is how we solve such a question. In the third question, if the image formed by a lens for all positions of an object placed in front of it is always erect and diminished. This is exactly what I said just a few moments ago. What is the nature of this lens? Come on. Just now we discussed it in the previous question. Yes, it's going to be a concave lens, because a concave lens always forms a erect and diminished image of the object. So you have to draw a ray diagram to justify this answer. So you'll be drawing this ray diagram, the one in which we place the object anywhere in front of a concave lens. If the numerical value of the power of the lens is 10 diopter, what is the focal length? So focal length in meters, always remember this, because this is the part where maximum confusion is there, is the inverse of the power, or you can say power is the inverse of focal length in meters. So in this case, it's going to be 1 upon 10 meters. Now if you convert it to centimeters, you multiply it by 100 and you get focal length equal to 10 centimeters. So when we say Cartesian system, it means according to the proper conventions. Now since it's a concave lens which has a negative focal length, so it has to be minus 10, and that is how we justify it according to the Cartesian system. I hope it's clear to everyone. The fourth question, we wish to obtain an equal sized inverted image of a candle flame on a screen kept at a distance of 4 meters from the candle flame. Now remember that screen is the place where you will get the image, and the candle flame is the object. That means 4 meters is the distance between the object and the image, which according to the question is equal sized and inverted. Now for this you need to be very thorough with your ray diagrams, because there is only one situation in which you get an equal sized and an inverted image, and it's always formed by a convex lens, because a concave lens always forms a diminished image. It never gives you an image of the same size. And now you have to tell what should be the focal length. So if this total distance is 4 meters, obviously your lens would be in the center. So this makes it 2 meters here and 2 meters here, because the entire thing is 4 meters. So we know that the midpoint, that is somewhere here we have F1 and somewhere here we have F2, that makes it 1 meter. So this is going to be 1 meter, right? So what should be the focal length of the lens? It should be 1 meter. At what distance from the candle flame the lens be placed? It should be 2 meters. Draw a label diagram to show the image formation in this case. So this is the diagram that you'll be drawing for this one. Clear? If it's not clear, you can watch this solution once again. The fifth and the last numerical for this video. An object is placed at a distance of 60 centimeters from a concave lens. So U in this case is negative 60 centimeters. Focal length is 30 centimeters. Now since it's a concave lens, the focal length would be negative. Use the lens formula to find the distance of the image from the lens. A very simple question. You just have to calculate what is V here. Use the formula 1 upon V minus 1 upon U is equal to 1 upon F. So 1 upon V would be equal to 1 upon F plus 1 upon U. Substitute the values here. 1 upon F is 1 upon minus 30 plus 1 upon minus 60. So when you take the LCM of 30 and 60, you get 60. This makes it minus 2 minus 1. That makes it minus 3 over 60. So your V would be minus 20 centimeters. So that is how we solve this. So I hope these few questions will help you out. And don't forget to practice these numericals, because yes, practice is the key to success. So that brings us to the end of this video course on the chapter Light, Reflection and Refraction.